Every cosmological model we have relies on a specific set of assumptions about how the early universe formed. But recently, a single point of light has begun to suggest those assumptions might be incomplete. For decades, the standard model, known as lambda cold dark matter, has been our most reliable map. It successfully explains how matter clumped together over billions of years to create the massive, web-like structures we see in the modern universe. However, when we look closer, the math starts to diverge. The standard model struggles to account for why galaxies take on specific shapes, why their stars form as quickly as they do, or how their central supermassive black holes reached such staggering sizes so early on. These discrepancies are personified by GSZ11. It's an irregular galaxy located 31.5 billion light-years away, observed as it existed 13.1 billion years ago, placing it within the first few 100 million years of cosmic history. Within this ancient structure, we see intense starburst activity, a violent, rapid birth of new stars, swirling around a dense, massive core. That core holds a black hole estimated at 8 million solar masses. Under our current timelines, there simply hasn't been enough time since the Big Bang for a black hole to grow that large, or for a galaxy to become this active. Because GSZ11ro exists in a state that the standard model cannot produce, it serves as physical evidence that our current understanding of galaxy formation requires a different structural framework. One proposed solution is Cosmic Helium Evolution Theory, or CHET. This framework moves away from the idea that hydrogen and dark matter are the only primary drivers of the early universe. CHET argues primordial helium-4, forged in the extreme heat of the Big Bang, acted as the essential spark for the very first stars. In this model, the abundance of helium-4 regulates the entire life cycle of a galaxy, dictating its eventual shape and providing the fuel needed to rapidly build supermassive black holes. To test if helium really is the architect of the early cosmos, researchers had to capture and analyze the oldest starlight ever detected. This analysis utilized the Hubble Space Telescope alongside ground-based observatories like Keck, which use massive mirrors at high altitudes to peer through Earth's atmosphere. By isolating a specific wavelength range between 3,000 and 7,000 angstroms, scientists could measure the exact chemical makeup of GSZ11, calculating its ratio of helium to hydrogen and its low levels of heavier metals. This data provided a raw, unmanipulated chemical signature, allowing researchers to see if the predicted math of CHET matched the physical reality of this ancient galaxy. The researchers performed a blind test, applying the pure CHET model to the GSZ11ro data without adding any extra variables or adjusting the equations to fit the results. This chart compares predictions against observations. Morphology. CHET predicted and observed an irregular shape, 100% match. Black hole mass. CHET suggested 8.1 million solar masses versus 8 million observed, 98.75% accuracy. Helium-4 abundance, 24.5% predicted versus 24.2% actual, 97.42% accuracy. Achieving this level of precision without any post-observational adjustments suggests that CHET isn't just a mathematical coincidence, it is a functional description of the early universe. The data from GSZ11ro indicates that the hydrogen-centric era of astrophysics is no longer sufficient to explain the distant past. Primordial helium-4 has emerged as a central driver of cosmic structure, star birth, and the growth of the largest objects in the universe. While the current results are a milestone, the model will be refined by adding complex physics, like thermal pressure and neutrino interactions, the way these nearly massive particles transfer energy and influence the movement of cosmic gas. By accounting for these specific external forces, researchers project that CHET's predictive accuracy will likely climb above 99.9%. By following the behavior of primordial helium, the mechanics of how the first galaxies were assembled and how they evolved finally become clear. Return to MDU to explore more of the cosmos. Like and subscribe.